Welcome to Comp 2503, Programming 3. The purpose of today's lecture is on the basic, to give a basic introduction to data structures and algorithms, kind of what we're covering in this entire course, to give you a beginning grounding of what you will actually deal with. So instead of seeing my face for the rest of this time, we will switch to the slides and get started. Okay. Now, with my slides, I tried to include these too long didn't read videos that I'm able to find that I think give a good first summary of what I'm going to cover. For the online videos, I will play these fully out. In lectures, I will only play selective ones.
Hey everyone, welcome back to my channel. So today I'll be chatting about a super important topic. I'm going to be talking about the 4 beginner data structures that you need to know as a developer. Whether you're looking to interview at a top tech company or you just want to level up your programming skills, having a solid understanding of data structure is such an important skill you need as a developer. So what is a data structure and why is it so important? Data structures are a particular way of organizing data in a computer so that it can be used effectively. Just like in real life, we determine the best containers to store certain items based on what they are and how we plan to access them. The same is true for data structures. Depending on the type of data you have and how you want to access it, you need to find the right data structure to help you organize and perform any sort of operation on that data. But there is no perfect data structure. Every data structure has its strengths and its weaknesses, and you have to consider the trade-offs before deciding which one to use. So the way we understand the strengths and the weaknesses of a data structure is through a mathematical concept known as Big O notation. Big O notation, simply put, represents the worst case runtime or space requirement for a data structure or algorithm. So as your input size grows, how much longer does your algorithm take to run, and how much more space in memory does the algorithm need? So the most common Big O notation that you'll see is constant time, and that just means regardless of the input size, the runtime stays the same. You also have linear time, which means as the input size grows, the runtime grows linearly. Quadratic time, which means as the input grows, the runtime grows quadratically. And finally, logarithmic time, which means that as the input size grows, the runtime grows logarithmically. So let's start with the most common data structure that you're going to see, which is the array. An array is a linear data structure of fixed size used to store the same type of elements at a contiguous location. The locations are also called indexes, and in a computer, the index represents the location of the object in memory. Visually, an array reminds me of an egg carton and has a lot of the same properties. So just like egg cartons, arrays have a lot of great benefits. So let's say that we're looking for a specific egg and we have the index of the egg. We can quickly get the egg that we're looking for without having to access all the eggs to find the egg at a specific index. So this basically means that one of the biggest advantages of an array is that access happens in constant time. But like egg cartons, arrays have some important limitations that you have to consider. The first limitation is the fact that arrays are a fixed size, just like egg cartons. If we wanted to add more eggs to an egg carton or we wanted to add more items to an array, we really can't adjust the size of the carton unless we have a dynamic array or an array list. Another disadvantage of egg cartons is the fact that searching for an egg is really slow. Let's say we wanted to find the largest egg, but we have no idea where that egg lives and we don't know its index. At worst case, we would have to start from index 0 and go through the entire carton until we found the egg, and this happens in linear time. The next most common data structure that you're going to see, but mostly during the interview process, is a linked list. A linked list is where we have a node, and that node usually stores data. For example, it could store a number value, and those nodes also have pointers, and the pointers do just what their name implies. They point to other nodes. The pointers are what basically chain the nodes together in a linked list, and that's what constitutes as the linked part of a linked list. And the pointers also represent the address or location in memory of the connected nodes. Visually, a linked list reminds me a lot of connected keychains. Because the links are pointers, this provides us with some really cool advantages over arrays. If you want to add a specific node to the linked list, all you'd have to do is just change the pointer in a linked list, just like all you would have to do in a keychain is just unhook the other keychain. So insertion and deletion happen very quickly, and they happen in constant time. Another main advantage of a linked list is the fact that there is no discrete size limit. Unlike an array where you usually have a size and then you kind of stick to the size, with a linked list you can continue to add nodes and there is no fixed size, so you can add a node whenever you'd like to. Just like other data structures, linked lists have disadvantages that you want to consider. Because linked lists have pointers, this means that you have to use extra memory to store the pointers. Another disadvantage of a linked list is the fact that searching is kind of annoying. Just like with an array, searching through a linked list to find a specific item can be difficult. You have to go through every single element until you find your target. And this happens in linear time. So before we move on to the next data structure, I want to thank my sponsor for this video, Educative. Educative is an interactive learning platform. I actually took the Grokking the Coding interview course last year when I was job hunting from those data structures. The first of these data structures is a stack. A stack is a linear data structure that is optimized for the LIFO retrieval order. And if you're not sure what LIFO stands for last in, first out. And this is basically the major purpose of a stack and what the stack is optimized for. A stack reminds me of a Pringles container. Just like a Pringles container, if you want to take a Pringles out of it, you can only take it from the top. And this is known as a pop function. You're popping the Pringles from the stack. And if you want to put a Pringles back into the container, this is known as a push function. You're pushing the Pringles back on top of the stack. Stacks are just optimized for this LIFO retrieval order, and this is their biggest advantage. But just like the past few data structures we've seen, search is a huge con and a huge disadvantage of a stack. Searching for a specific item isn't the best use for a stack. If there is a specific Pringle that you wanted to access, you would have to go through every single Pringle until you actually found the Pringle that you wanted to access. Same with the stack. If there was a specific item that you wanted to access in the stack, you would have to go through every single item until you got to the item that you wanted to collect. Another disadvantage of the stack is if you need a different retrieval order. Let's say you wanted to get the first item in instead of the last item that was put in. This is where a different data structure comes in, which is known as a queue data structure. A queue is just like the word implies. Just like a queue or a line of people if you're in the US waiting for something, there is a specific order that happens when people are in a queue, which is the first come, first serve, and this is known as FIFO. When you add to the queue, this is known as on queue, which means you add to the back of the data structure. Let's say that you wanted to take away from the queue. The way you take it out is through something called dequeue, which means that you would take from the front of the stack. And this all happens in constant time. And this is the main advantage of the queue is its FIFO retrieval order. But just like we said with all of our other data structures, there are going to be some disadvantages of this specific data structure. And that disadvantage, like we've seen with all of our other 4 data structure, is search. Searching for a specific item in the queue can be a little tedious. Let's say the barista wanted to access a specific person in the line, like the man in the suit. He needs to serve everyone or make everyone has been dequeued before he can talk to the man in the suit. And in worst case, this happens in linear time. So there you have it. Those are the 4 beginner data structures that you need to know as a developer. And make sure to stay tuned for part 2 of this series where I'll be going through more advanced data structures that you need to know as a developer. And thank you for watching. If you found this video helpful, make sure to give this video a thumbs up and tap that subscribe button. it's Bacola and welcome back to my channel. So today I'm going to be talking about probably one of the most important parts of getting a job as a software developer, and also an important part of upgrading your skills as a developer as well. And that is learning and understanding data structures and algorithms. I'm going to be real with you. The best thing I did for myself during my transition process was taking a data structures and algorithms class. And that class has paid off dividends. The truth is, a lot of questions you're going to get asked during the interview process are based on data structures and algorithms. So in this video, I'll be sharing the strategy that I use to learn and master, I don't like the word master, to learn data structures and algorithms and to just really make sure that it's stuck with me going forward. In this video, I'll be sharing a 3-part strategy. It's going to be a little thorough, but I promise you if you can do all 3 steps in this strategy, you'll create a really strong base for yourself when you're applying for jobs, and also you'll just have a strong base for data structures and algorithms going forward. There is a study in 2016 by TripleByte shared that during the interview process, people from untraditional backgrounds, specifically boot camps, their biggest weakness was in data structures and algorithms. Because untraditional folks like me haven't taken or usually don't get access to taking data structures class, it makes it kind of difficult for us to do well during the interview process. So while you're making your transition, I would highly recommend take a data structures and algorithms class. Take a lot of time to really learn the topics of it and make it stick. So without further ado, let's hop into the video. But before I hop in, I want to thank my sponsor FastHost for sponsoring this video. I'll be giving more details about FastHost in the video class and gain general data structures and algorithms. When I was doing the process, the class that I chose to take was this UC Berkeley Data Structures and Algorithm class. This class was very thorough, it was pretty difficult, but it was a really good class for really understanding and learning data structures and algorithms. I also read these 2 books, but I felt like I preferred the class because I learned a little bit easier from videos rather than reading books. So my first step in making it really stick is if you're from an untraditional background and you have never taken a data structures and algorithms class, I'll leave a couple recommendations down below. While you're taking the class though, it's not enough to just take the class. It's really important to take really detailed notes on the class. So the next part of this part 1 of really understanding and learning data structures, I'll be talking about how to structure your notes so that you can really gain a lot from the class. When you're writing your notes, please do not use anyone else's notes. There are a lot of great notes online for learning data structures and algorithms, but if it's your first time learning the topic, I would try to take your own notes on the topic and then maybe in the future reference other people's notes. So when you're taking your own notes, these are a couple of things you want to make note of. You want to have a brief overview of the data structure or algorithm. So in plain English, explain like you would explain to a 5-year-old what this data structure is. Then what you want to do is you want to have some sort of, especially for your advanced data structures that are a little bit harder to explain with words, you want to actually have either coding visualizer or the actual picture of the data structure right next to the English description of the data structure. Now going to even more important parts, after you have an overview of the data structure, you have an image of the data structure, the next thing you want to do is you want to explain why this data structure exists. I know this is kind of weird and abstract, but you want to know why would you choose this data structure over other data structures. So you can either have a pros and a cons list about why this data structure is a good data structure, what are the weaknesses of this data structure as well. You also want to make sure to write down what is this data structure / algorithm optimized for. We all know that data structure exists to organize data and to maximize and minimize space. And data structures are really good at different operations. Some data structures are Welcome back to my channel. So explain like you would explain to a 5-year-old what this data structure is. Then what you do is you want to have some sort of, especially for your advanced data structures that are a little bit harder to explain with words, you want to actually have either coding visualizer or the actual picture of the data structure right an overview, you have an image of the data structure, the next thing you want to do is you want to explain why this data structure exists. I know this is kind of like weird and abstract, but you want to know why would you choose this data structure over other data structures. So you can either have a pros and a cons list about why this data structure is like a good data structure, what are the weaknesses of this data structure as well. You also want to make sure to write down what is the data structure / algorithm optimized for. We all data and to maximize speed and optimize space. And certain data structures are really good at different operations. Some data structures are better with retrieval, insertion, access, deletion, etc. You want to make sure that in this second part, to really deepen your knowledge, you know why this data structure actually exists. Next thing you want to do is you want to have a chart explaining the big O of the different operations for this data structure. What's the big O of the insertion? What's the big O of access? What is big O of deletion? You want to make sure that you have the big O analysis of every operation written down for this data structure as well. Now, finally, the last step of taking your notes for this data structure and algorithm is actually writing algorithm, coding it from scratch. By coding it from scratch, this really helps round out your notes because not only do you have the English version of what it looks like, picture version of what it looks like, you also know what in code. And this for me really helped a lot of data structures and algorithms stick for me. It's a very tedious process, but I promise you, if you build a linked list from scratch and someone asks you about insertion for a linked list, you will know that it's constant time because you've actually written the function that actually inserts a node in a linked list. So it's another way of making sure that you really solidify the knowledge and you really solidify the information. Great, so we've written these structured notes. Now let's go on to the next step. So before I hop into the next process, I do want to make sure to give shout out to my sponsor. Thank you, FastHost, for sponsoring this video. If you're not familiar with FastHost, Ultimate Tech Bundle. The next step of the process is creating flashcards based on your notes. Like I said, your notes are going to be very important, and your flashcards are going to be also a way of really memorizing and deepening the knowledge of these data structures and algorithms. Using flashcards can really help you with spaced repetition. This is a way of just kind of taking your learning to the next step because you have a general overview of each topic, but now you get to practice the knowledge of these different topics through spaced repetition. It's just another way of just making sure that you can memorize information. What it does is that the information that is newer, you might not have learned it, or the cards that you don't always get right are the cards that you see more frequently so that you can learn. But the cards that you have gotten right very frequently and are older, those are the cards that you see less. So I'd recommend just having flashcards because this really helps solidify your knowledge. And you can also come back to them a couple years later when you're applying for jobs again. After you've gotten a lot of the cards right and you feel like you really understand all the data structures and algorithms, now you can move on to the next process, which is actually practicing questions to make sure you really understand these data structures and algorithms. A wise philosopher once said, "A leak code a day keeps unemployment away." And I really kind of stand with that, even though I don't practice it at all. I have better things to do. So this next part of the process is just sort of applying the knowledge that you've gained. You're just going to take the time to use either LeetCode, or you can use any of these two books to practice. I have Cracking the Coding Interview over here. It's a great book for practicing interview questions and just practicing your knowledge of these data structures and algorithms. And then I also have this other book, Elements of the Programming Interview in Python, and this can be another way of practicing the knowledge that you've gained. And while you're also practicing, if there are questions that are really difficult, you can always go to YouTube. I'm going to leave a couple people who are very helpful, who do a great job explaining different topics down below. So thank you guys so much for watching. I hope this video was helpful, and I hope this video gave you just a very study method to really make sure that data structures and algorithms stick. I want to wish you guys good luck during your process. I promise you, it is not brain science. You will be able to figure this out and you will be able to learn. Thank you guys so much for watching this video, and I'll see you guys next time.
I apologize for the little blip while doing the videos there, but I think I recovered fast enough. So that was a little bit longer videos from there, but I thought they were both really good first introductions. The first one gives you a feel for idea, just data structures, gives some key terms within there, and the idea of choosing the right data structure and algorithm to use. And we'll even get into choosing the right implementation of it and what impact that has. And our last video about practicing. That since this is a core course for everyone who's here, that like understanding this material can be a benefit. Can I say that every single job that you'll have in the future will involve everything from this? No, but it doesn't mean that dealing with complexity isn't an important thing in expanding your knowledge and expanding where you will work and what you could possibly do, and beyond just a job, your own knowledge. So, starting in on my own notes here, like, what are data structures? Like, a data structure is a particular way of organizing data in a computer so that it can be used efficiently. It's a very general term, but we're all used to that from that beginning programming. We need to store information, and then we will access it and modify it to accomplish our task as we go through. And you've dealt with that in the earlier programming courses, but now coming into your data structures course, you're stepping out from just being your starting language, but dealing with something that's a little bit more universal to programming and computer sciences and engineering in general. Is, well, once we have all this information, how are we going to organize it in a way that then makes it efficient to retrieve, access, modify, and do the work depending upon the algorithm and problem that we are trying to solve? And it's the whole point of why you have this course. So different kinds of data structures are suited to different kinds of applications, and some are highly specialized to specific tasks. So before this, you've kind of used previous storage like variables in your arrays, which are general purpose and used for a lot of things. But now you've got to start learning, okay, well, when I have this data structure, what is its advantages, disadvantages? Where is it best to actually use this? Where is it bad to use this? What variations are there? How can I change things? Time? All those things need to be taken into consideration for what's useful for the context that you're working in. We're going to be coming at the data structures generally from the point of, well, here's the data structure. Let's understand the advantages and disadvantages and get into some basic applications. Because we have limited time in the course of this semester to go through everything, and this is just one data structures course, and it should just be the beginning of your journey to work with data structures that you can keep expanding on beyond this course. But take this into account. So what are they? Like, data structures provide a means to manage large amounts of data efficiently. And that's going to be the bigger thing. That a lot of times, even in the assignments course, there'll probably be small data sets, small amounts just to begin with to make it feasible what we're doing. But like in modern day times, like there is tons of data and tons of information out there. And so little changes that speed things up and make it better can have a huge impact on an overall program. And it's one of those factors that's in there. And so they allow us for that efficiency, but they also allow in a way that, well, if we organize it this way, it helps us solve the problem easier. And that may be hard to see now, but as we get into the data structures and more examples, you'll start getting a flavor for it. So usually efficient data structures are a key design to efficient algorithms. As I said, like, well, we can store our data, and when you're dealing with your basics of arrays and variables, you don't really think about that because you just have to store that data, and it seems like such small access. But really, once programs start growing larger and the amount of data that they start growing grows over time, let's say even the beginning and a program's running longer, more data is collected or has to do more work, well, the way you store it will affect how long it takes your algorithm to actually run and your overall program itself and to solve anything. And sometimes when we're dealing with nanoseconds or faster, depending on the industry and what you're working on, this can have a massive impact. Even other things that you're dealing with, if you're going into your video games and the slowdowns and different impacts that could be causing that between hardware to software design and taking this into account, is the change of a data structure could have an effect on the efficiency of an algorithm. And this can go even beyond just changing the data structure. It could be one implementation of it versus another, because data structures can be implemented in the same exact one, can be implemented in multiple different ways and by different people. And so evaluating, well, what is the most efficient way for the operations we're using to come together to try to make a more beneficial environment for our algorithms. The implementation of data structure usually requires writing of a set of procedures that create and manipulate instances of that structure. So if you've dealt with object-oriented programming, this sounds similar, but the idea is like, well, you have something physically storing the data in some way, and then you have a list of specific operations where each operation does one piece of work on that structure. So either adding, removing, retrieving information, updating stuff, things like that. And you can think of these operations like your methods or methods for your object that you're calling, if this is an object-oriented example. But really you just have these operations that work on that data structure itself. So the efficiency of a data structure cannot be analyzed separately from these operations. So you have the internal data and anything else beyond that, but you also then have to look at each operation, how long they take, and evaluating it as a whole structure, and which operations would be called the most for your program, because if that one is very inefficient and it's called the most, then your overall program will be inefficient, and maybe that's a bottleneck point that you need to go after and try to fix up. Now, for this class, and you'll see other times online, is that we have a new term to learn in this case, and calling this an abstract data type. Now, when I'm talking in this realm, I'm not talking about syntax and semantics or Java, C++, Python. This isn't something that's internal for programming languages. We're dealing with more computer sciences and dealing with the idea of data structures, which is not just one language like Java's construct. This is a programming construct that you can take to multiple different languages beyond that. So when I talk about an abstract data type here, I'm not talking again about syntax. I am talking about this abstract idea that you need to deal with. And this is just to make a connection with data structures and those operations, is that when we talk about things like a stack, a queue, a list, or a linked list, that's not just a Java thing that you could see and implement. You can see in C++ and Python. But with all these ideas is that, well, if it's a stack, it should have these common operations generally named this way, and you should see that throughout whatever language you're working with, and it's a good structure for yourself to follow. So a data structure that is defined indirectly by the operations that may be performed on it and the mathematical properties of those operations. So that's where you have to see when we talk about an ADT of a data structure, we're really just talking about what are the operations that we should expect to see if we're implementing or just using this data structure in our program itself. So now taking a step to the side before we go further, we're talking about data structures and algorithms. And like, if you've been doing programming, you've heard the term algorithm before, being that it's a finite sequence of steps that solves a specific problem. And that's the very generalized definition I'm giving just for this course. And so being that you have some steps that the program goes through from beginning to end, it will solve the problem and stop doing whatever reaction that you're doing. That's an algorithm. A very general definition. So again, you can see like algorithms generally represent recipes. So like a cooking, baking recipe. Recipes tell how to accomplish a task by performing a number of steps and what you should do. So to bake a cake, the steps are generally maybe preheat the oven, mix your ingredients together, pour into baking pan, and burn the living bleep out of it because you forgot it while you've gone to do some other task or something like that. Who knows? But that's the idea, that you would follow those general steps. And that's what a computer is doing when you're giving it your algorithm, is that it's following those steps in the way that it understands each individual operation, and you as the coder are having the overall vision of it. Before computers become sentient and us as programmers become completely obsolete, if that's even ever possible. But that's a different topic. So however, algorithms is a technical term with a more specific meaning than recipe. And calling something an algorithm means that the following properties must be true. And this, I'm just including this to get you that feel like this is more of the kind of technical definition of an algorithm when we get into data structures. Like an algorithm is an unambiguous description that makes clear what is to be implemented, expects a defined set of inputs to come in, produces a defined set of outputs, and guaranteed to terminate and produce a result. Now, these are definitions you need if you were to go into other theory courses in programming and data structures and complexity and stuff like that in the future. It would go beyond this and you get the idea of the halting problem and stuff like that. But for us here, we're just going to be working with algorithms that we know are guaranteed to terminate and stop and produce a result in the actual end. Now, there are several different characteristics of an algorithm that are useful to know. So, does an algorithm actually exist to perform a given task? Now, what this means here, especially when we're coming to data structures and algorithms, is that before you've been writing your own algorithms, solving your problems, but when it comes to a lot of other things out there, there are classically named algorithms that other people have created that help solve a problem that you can then implement. For example, you could look up Dijkstra's algorithm, which deals generally with graph data structures, and it helps finding the shortest path between 2 points on there. But that's where you get those classically named. So you have to look, even when you search for are there other solutions in the general algorithms out there that help solve a problem, and how can you modify them? There's a whole world of these out there that you can start looking into. If someone proposes an algorithm to solve a task, are we sure that the algorithm works for all possible inputs? So as usual, it works here, but are there problems with your implementation? Do you need to test it more, and so forth? How long does the algorithm take to run? How much memory space does it require? In your first programming classes, you probably didn't think about this a lot. You were just worried about solving it, handing it in time, the fact you had 5 minutes before it's due and you need to submit it, and you're panicking. It's more of those things that you're worried about for time. But when it comes to your own program, you probably weren't really thinking, well, how long is this going to take to finish running and deal with all this information? Because you were dealing with smaller programs. So for some implementations and products that you may work on in the future, you need to worry about that with the algorithm you're choosing to use or that you are writing yourself, you need to know, well, how long could it take to run? And what about in that worst case from here, and having some kind of idea of how that works. How much memory does it take up as it runs? Is it going to keep taking it more and more memory, which is going to start causing problems and so forth? And does that even matter to you? Now, once we know it's possible to solve a problem with an algorithm, a natural question is whether the algorithm is the best possible one. Can the problem be solved more quickly, or is there a different way of doing it? Is there a different way to organize our data using a different data structure, which then changes our algorithm and makes it run faster, or is easier to read, or uses less memory, and so forth? So these are all things you need to take into consideration, and then you also need to take into context of the program you're working on and other factors that may come into play, especially if there's money in play with developing this. What can you actually do? Now, here's an example of a basic algorithm, probably something you've had to deal with before. So, problem. Given a list of positive integers, so no negative numbers at all, return the largest number that's in that list. And when we talk about list, this means a list that's of some finite size that is given in, and we just need to find what is the largest number in that list. And this would be a list where it's not consecutive numbers, they're just, you don't know from the algorithm what's coming in other than some random assortment of different numbers, and you're supposed to give back that maximum one. So, boom. Inputs. A list of L of positive numbers. This list must contain at least one number. Asking for the largest number in a list of no numbers is not a meaningful question, but some people like to ask it. And outputs it gives back is a number n, which is the largest number in that list. So here is one possible implementation of the algorithm, just using some very basic like pseudocode. So step 1, set a variable max to 0. We need this in the beginning because we know they're positive integers, and so the smallest you could have from that is 0 if you're including 0 in that set of positive integers. So we just know that's the smallest you could get, and if it's all zeros in there, it's also the maximum. So a good starting point. For each number x in the list L, compare it to max. If x is larger, set max to x. And you keep going through this for the entire list, and you know you're going to be guaranteed that max is now set to the largest number in the list. So this is a general algorithm like you're used to. You know the computer doesn't have an overall view of everything to instantaneously make a decision from seeing all the numbers. It steps through it one by one. So you just have to go through it one by one and see, hey, is this bigger than what I've seen? No. Okay, throw it away. Is it bigger than the next one? Is it bigger than what I've seen? Yes. Okay, keep it. And you know by the end of that process that you will have found the largest. But one thing about this is to know, well, yeah, that finds the max. That's an algorithm. Maybe there's a faster way of doing it, but this is on a random list of integers. And so to find it, we know we need to go through every single element in that list. So if the list has got 10 elements, we need to go through 10 times to find it. If it's got 1,000, we need to go through 1,000. If it's got 1,000,000, 2,000,000, a trillion, we need to go through each of those to find the actual max using this algorithm. And so it has this kind of growth and complexity to it as you're dealing with it. An algorithm. The bigger thing from this is, the last one like we had, is that an algorithm works with a data structure. So the use of different data structures can result in different algorithms for the same problem. And the idea is that steps. Well, because like imagine that last one that we just had for finding the max is that it was given the data structure, i.e. an array of those positive integers, and it needed to step through that. And so you needed then that loop to step through on each individually, and that impacted how the algorithm itself worked because, the list that were actually given itself. What if we had a different data structure that could organize the numbers as they were given into the list, and then it became even faster later on to always access what is the maximum one, which is like a max heap if you want to look into it yourself. So bringing this all together, and the point I've been trying to make is that when you look at your overall program now, beyond just your blood, sweat, and tears and whatever else you've put into it, you have to think that it's also built up of all the algorithms and all the data structures that you were using to make that program. And then also all the algorithms and data structures that the people who wrote the libraries that you may be using or other tools used to solve that problem for you to get over to this bigger program. And all these things have an effect. The algorithms you use, the data structures then that you use, and it all just funnels down and becomes your overall program that you are using. Now, throughout the course, we're going to be going through, again, a range of different data structures, and it's not everything that is out there in the world. And we can't. There's so many different types and variations of these, and the point of this course is to more give you a general overall view and introduce you to some of the classical ones we start with. And this picture here is just kind of pictorially showing similarities where these data structures came from ideas. Things like queuing up in a list, or stacks overall for information, or quick lookup and retrieval of information. So queues, stacks, hash tables we're dealing with here, basic lists like we'll have for arrays or linked lists we're working with. We have different chart things. We're going to get into trees and stuff like that, and all the variations of trees you can get and what that does for you. And then you could also go into things like this map is supposed to be representing the idea of graph data structures, which is kind of a step up from what you're dealing with for trees. We won't really be covering that in this course, but I do highly suggest that if you enjoy data structures and want to do more, look into graphs and graph algorithms. There's a lot of stuff that's out there that's very fascinating. Now, I've mentioned some of the basic data structures that we have seen before here, and like you start this in your first programming course, any programming you're going to learn before doing any outputs, like you start learning about variables, which is just one chunk of memory that holds one piece of information for you that has a specific type associated with it to tell the computer how to access that information. So that's your starting building blocks. That's where you read in inputs from a user, add stuff together, store that result back, check that number with your conditionals, use it as part of a loop, and whatever else you want to do with that. And then stepping up from there is where you start getting to your arrays, the 1D arrays, your 2D arrays, and so forth, which then just takes that idea of one independent variable and gives you access to a variable that has these independent slots. So a variable that has all these little variables inside of it, like a bookshelf or so forth, that gives you a linear kind of structure. That it takes from these random variables, but it gives it that, okay, well, you have something that could be considered the front and back end of the array, or the first and last. You have then something that becomes sequential from it, that you have like 0, 1, 2, 3, 4, 5, that you have some sequencing, and then you can start using that linear structure to do stuff. So storing records, looking them up, keeping class lists, whatever you're doing when it has to be a list of information that you're keeping together. So, and the other key thing from arrays that are the basic type, we're not talking about array lists, which is an object and stuff in Java, and other languages like Python that have dynamically growing arrays or lists. We're thinking the idea of arrays, the basic level of being fixed size. That generally you have to manually expand yourself, or if the language does it for you behind the scenes, that expanding is actually being done, and you need to be aware of that. So those are the first ones we dealt with. Now, coming back to that term we had earlier on, we talked about data structures and the fact that they have operations associated with them. You remember we have this term ADT, or abstract data type, which is just, again, that when we talk about a data structure in general beyond languages, we talk about it of that it has data that stores, but we talk about the operations that we use to access that data. So again, ADT, a specification that describes a data set and the operations on that data. Each ADT specifies what data is stored and what the operations on that data do. ADTs are independent from any programming language, so this isn't like, oh, I know this is the syntax for it. This is just a general term that we talk about stacks, we talk about trees or graphs and specific things like that, that we can say, well, there's this type, you do this with it, and then you can go and physically implement in the language or find a library that implements it for you. And it's possible to have different implementations of the same ADT. It's just like you saw the same one. We know a stack has to work this way, but how someone gets that to work behind the scenes could be different. But the operation of, say, as we're going to talk about in a second, of a push or pop, we have to know, well, it works this way, and this is what it gives back for someone who's calling that operation, and then someone else just deals with it differently behind the scenes for stuff. Maybe a weird analogy I could think of this is if we go to fast food chain restaurants and we say pick one of them. You know, when you go to one store in one location, you're generally going to be ordering the food one way. You go to the teller and then they send the order to the back. And if you go to a different store with the same chain, they're probably ordering the same way from the kiosk or whatever. Now, it could be different as maybe the steps of how they go about what order of getting stuff behind the scenes. When they go get your fries, get your drink, get your burger, get whatever you want from there, that maybe that's a different order, and how they prepare it's different order at every different restaurant, but the end result is you getting your meal properly back. And that's a very vague analogy. And so think about this as being the ADTs, is that we know the idea, say, of a stack. We know it has these operations. We as the coder are using a stack to solve our algorithm call, push, and pop. But you could have coded the implementation behind the scenes yourself or use someone else's library, and it could be different along those terms. So each is evaluated based upon execution time and memory usage. So when you come back, is we have different stacks, but you want to worry about, well, okay, maybe this one, that person's implementation for the pop was a little bit slower than I would like. Maybe there's a better way to implement it. And we're going to get to these two different sides of the internal, external views of data structures, where we build some ourselves, or we just use ones that we're given to then solve a problem, and so forth from there. But it's why we need this abstract data type as a term to talk about it independently from languages. So stacks, I've kept mentioning them here. Now, stack is a linear data structure, so like an array which goes 0 to 1, but you can put stuff anywhere from there. But elements are stacked on top of each other is the way you visualize it. So, and this is where you get that LIFO, last in is the first out. So the last thing you put on there is the first thing you take out. So analogy like plates and other stuff with that. So only the last element can be accessed, so it's always on the top of the stack, and you're not jumping below to come back to that. Now it sounds weird, and this is the visualization of it, how you would implement that. You could use an array or linked list or other stuff like that, but that's behind the scenes. But for right now, we just think of, okay, well, I push something on to add it onto the stack. I pop to take something off. When I push something on, it goes to the top. When I pop anything off, it just comes off whatever is currently on the actual top right now. And so you're always going up and down from there. So a common analogy of a data stack is a pile or stack of plates, say in a canteen or cafeteria. Plates are stacked on top of each other. A customer takes a plate from the top, so that'd be like that's a pop taking it off. And if for some reason they wanted to access the second plate, they would have to remove the other ones from the top. So they're like, there's something gross in this top one. You got to take that top one off first. So you pop it off, then you pop off another one to get the plate that you actually want. Maybe someone's cleaning them and they add it back on, so they will push them on one at a time. And again, just an analogy, so maybe you can get a little bit more of a visualization in your head. So here, as an AT, is maybe like something we're used to, making it look like an actual coding language, but just getting a little closer to here. So a way to use pseudocode-esque methods to describe the operations and inputs they expect. So push E, so place element E wherever you want in the stack. Pop, remove it and return it. Top, just returns whatever is on the top and doesn't take it off. Size tells you how many things are on the stack, and is empty tells you, is there anything actually, is the size equal to 0? Is there anything actually on the stack? Now, I'm talking about this fast, but what you should take into account when you're looking at this is I'm not talking about ints or doubles or floats or strings or specific whatever objects you're working with, because again, with this ADT, it's storing of data. And this data could be whatever you want it to actually be. So one data element, one object that contains everything or whatever you want. But the operations are still the same. Put it on, take it off. Doesn't matter if you change the data. And this is defining the general ADT. You could find out other operations in the future, but these are common ones that you will see for a stack. Now, we could implement physically in a language a stack ADT, say, as a Java interface. Now, if you don't know what Java interfaces are, don't worry. That's coming up in one of the next videos where we go over some new features of Java. But the idea of this interface allows us to design an algorithm that uses this stack but is not bound to one specific implementation of this. And this is a property. So this is an implementation of the ADT in Java specifically using interfaces and generics. If you don't know either of those, perfectly okay. I'm just introducing it so you can see it here. You will get it in future videos and be using it in future assignments. So here we see a basic implementation of what can be done. And the idea is when we're going here is that if I was just using a stack and someone else had built it and this is my job and that's done, and now I'm just using the stack to solve something as part of my algorithm, I don't care about how they implement it beyond the time and space complexity. And if that's been solved already, then I'll just go ahead and use it. So I just look at it as, oh, I call the push, I know where it's putting it, I know the pop, I know the top and size, and I know that if I push a bunch of things on, it's stacking them up. And then if I pop one thing off after that, it should give me back the last thing that was then put on. And I know that's very vague now, why would you ever use this? But we will have examples of that even coming up shortly here. Like in the next few slides / future lectures. So, oh, look at that. Next slide. Okay, applications. So this is part of, again, it's to give you that taste with data structures. Remember that they have good uses, advantages, disadvantages, and all of that. And you need to kind of think of these as knowing which is the right tool to use at the right time. So a stack data structure is useful when the order of the actions is important. So being that we need to sequence them, and that's important to us. So they ensure that the system does not move on to a new action before completing those before it. So the idea is that it's always the current one. If something else has to be done, well, it's stopped, it's gone on to the new task is finished, and then we're coming back to the original task, which hopefully, if you make the connection to how functions should work, will lead up to one thing of how stacks are used in all computers. In general, in the actual system you're using. So examples of where it could be used, say reversing something. By default, a data stack will reverse whatever is input. So for example, if we want to reverse the string hello world, we would push each character onto the stack and then pop each character off. because the idea is it would then be H, then E, then L, then O, and it's going all the way to the D. And so by the time we've gone through every character from the beginning to the end of the words, and we start popping anything off, it'll have the last character, and we'll be going back and giving the reverse order, which is important. Like, we're not going on to that. So it's just reversing something is a good use for stacks. Undo and redo in applications is that this could be useful for editors to implement the undo and redo functionality, is that the state of a program could be saved and pushed onto a stack when it's saving the current state, and then popped off when we want to do an undo of that sense of redoing an action. Instead of trying to memorize everything, is just keeping this, which may grow the memory more, but it may be useful for whatever operations we're doing, because you're always doing one action, the next. You want to undo, you want to go back to the previous action you're at. So that's nice for stacks. That's stack one action, stack the second, stack the third, stack the fourth. Okay, undo it. Okay, go back to the third step that was done, and then keep adding from there afterwards, and so forth. Backtracking. This can be used when writing an algorithm to solve a problem and choosing a path, for example, a maze. So the idea here is that, well, if you had a maze that your program was given and it had to search through it to find a possible path through it, which if you look into graphs and graph algorithms, there are actually known algorithms and data structures out there to help you with this problem already. But if we're coming back to this general one, we want to use a stack. One way to maybe find a path using computer is just to friggin' brute force it, is to take a step and go down every possible path. And when you hit a block where you can't go anymore, well, then you take a step back from it. And so it's backtracking. And the idea is, okay, well, if we're using a stack, is every time we take a step, we could push our current coordinates onto a stack. So take a step, push, take a step, push, take a step, push, take a step, push. If we come to an intersection with multiplications, we can pick one of them at random, and then we can, like, okay, keep doing that until we hit a wall and we say, hey, there's nowhere else to go. There's no other steps. I can't step forward, so I take a step back. Well, then all we need to do is pop off whatever is currently on the stack. So get rid of that and just go back to the previous step. And then we can check, are there more steps? Are there any places we haven't seen yet? So one quick idea. And now coming back to what I was kind of hinting at earlier on in all programming languages is the idea of a call stack. Programming languages use a data stack to execute code. So when a function is called, because you know that, you've written functions, you've written your methods, you know that when you call them, it goes and executes another piece of code and then returns back to where it was called. And so you can call that function multiple times. And so you need to know where you last were when you call a function. The system needs to know where was it last when it stopped the interaction before it goes to run the function, and needs to pass information, then come back. And this is called the call stack. And it's removed once complete. So you have your main, you have then functions that are called, that function completes, it goes back to where it was called from, so the previous step. And the idea here is that when a function's called, the previous location or instruction is then pushed onto the stack, and there's some other memory and things that are called the stack frame. The code is then executed, does its actual work, and then the function hits return or ends, and then, well, then instead of pushing stuff on, stuff is popped off, which would include the return address, and it jumps you back into the program where you left off last. So important reasons why there's stacks here, and why I chose this as a beginning example for you to work with. Now, where do we go from here? Well, this is the last of this one. It's already been a little bit longish of this part of a lecture. But the rest of the videos that are coming up will include things like new Java features. So things like generics and interfaces, and some specific things like comparable interfaces that we have in Java. Things that I just want to use for this course. We'll go over analysis of algorithms. So this is where you get the big O and evaluating things for its complexity, and a little bit of theory from this. We get into things like linked lists, so we can start learning about how to take chunks of memory and link them together to make our own structures, which then you start with linked lists, and then you go to trees, you could go to graphs. And then we'll get into specific data structure like stacks and queues and trees and hash tables. And then time depending, we'll get into then searching and sorting algorithms, which is a lot of computer science that's out there, and why there's so many different named specific algorithms that you will deal with. Other than that, I just want to remind you that you're awesome. And I will always keep disagreeing with you. If you think you're not awesome, I think you're awesome. We all struggle with our own issues every day, and I sure as hell don't know how to solve everything. But I know that if I first take care of myself, I can then take steps to take care of other people. And taking care of ourselves and other people can hopefully start making a difference of making this a better world that we can live in. And any little step that you take, I think, is a good one to better yourself, learn from mistakes and ignorances you may have held in the past, and grow and become a better person, and better to try to understand other people. So, a little off topic, but positive messages. I hope you have an awesome time going to the next lecture.